All right. So today we have John Terilla. I was excited to have John Terilla speaking to us because he, I guess, exemplifies something that we think is pretty important at Topos, namely taking ideas from pure math, category theory, algebraic topology, et cetera, and finding ways to make them useful. So John, please.
Thanks, David. Hi, everyone. I'm John Terilla. For those of you that don't know me, I'm a mathematician based at CUNY, the City University of New York, here in New York City. I'd like to thank David for the invitation to speak, and also take a moment to congratulate David and Brendan and everyone involved with the Topos Institute. It's really impressive what you've accomplished. I'm glad to be living in a world with a Topos Institute, and I'm looking forward to great things in the future. So the first line of the abstract for my talk that I submitted was that language is essential to being human. I don't mean to suggest that humans are the only species that communicate. I mean, the animal kingdom is filled with all manner of communication, monkey chatter, whale songs, mother birds flick their wings to communicate with their chicks. You have bumblebee dances. And as we're now beginning to understand, you have all kinds of communication in the plant kingdom too, albeit on a different time scale. But the idea that human language is somehow special is a belief widely held by experts across the sciences and the humanities. The linguist Noam Chomsky, quoted here, calls language the core property defining human beings. Here I quote the paleoanthropologist Ian Tattersall, who's based just a few blocks from here at the American Museum of Natural History. He says modern human beings process information symbolically, rearranging mental symbols to envision multiple potential realities other than the ones they occupy. And he adds that they also express the ideas they form using structured, articulate language, and that no other living creature does either of these things. Now, I'd like to emphasize this qualifying adjective living here. Emphasize living because as we see now in May of 2022, non-living computer-based large language models can acquire human language skills. So it's now at this pivotal moment when computers are learning language that I'd like to make an argument for rethinking language. Here's a picture of the paper from the Google group that introduced the transformer architectures in 2017. These are neural network models that employ a bit of engineering wizardry called a self-attention mechanism. That's why the paper is called Attention is All You Need. This transformer architecture made it possible to create what are the most advanced AI systems in the world today, these so-called large language models, sometimes abbreviated LLMs. These transformer-based LLMs have since advanced rapidly. Teams from Google and OpenAI and other groups quickly built bigger and better versions. You might know about some of them, like BERT, GPT, and so on. Here's this paper, Language Models Are Few-Shot Learners. This is by the OpenAI group, in which they announced their very large language model called GPT-3. This was posted about 2.5 years after the transformer was first introduced. What GPT-3 does is it predicts the next character from a piece of given input text. So it's iterating this next character prediction will yield a lengthy text continuation of a given input text. So it's a text continuation device, a kind of super sophisticated autocomplete. You can find plenty of examples of text continuations generated by these large language models, especially GPT-3 on the web. In the popular press, there's articles, there's probably been 4 or 5 articles in the New York Times about them. Anyway, you look for them if you haven't seen them. I think that the examples that people pick and publish are really impressive. Now, let's take a moment to talk about how a large language model like this is trained. So the model begins as a blank slate neural network. It's a collection of randomly initialized parameters that comprise a function that takes text as input and produces a possible next character as an output. Then the parameters are tweaked by a process that is, in essence, just trial and error. So during training, the machine is given a gigantic corpus of unstructured text data, which it learns from in an unsupervised way. So it reads a piece of text, say an incomplete text like this: the quick brown fox jumps over the lazy DO. It executes its function to guess the next character. At the onset, the guess would be random, and so almost certainly wrong, like capital V. But by using a simple formula, the internal parameters are modified little by little, improving the likelihood of a correct next character guess. And the model tries again with another piece of text. And this process is repeated many, many, many times, and as I said, in an unsupervised way until some level of success is achieved. So the model reads some text, tweaks its parameter, and repeats. It's basically trial and error. And amazingly, this works. So what can you do with a model after it's been trained? Well, a user can interact with the trained model by inputting a piece of text, presumably text that the model's never seen before, and then character by character, the model produces a continuation. So for example, if you input, I went to the grocery store and bought, the model might produce the continuation, a can of chickpeas. Now, the continuation is actually produced probabilistically. I said earlier that the model executes a function with a next character as output. It actually produces a probability distribution on possible next characters, like the letter A with 21% probability and M with 6% probability, something like that. So if you repeat the trial with the same input, the model will produce a different continuation next time. Like, I went to the grocery store and bought some cucumbers. But importantly, a well-trained model does not produce incoherent continuations like a new yacht, or I went to the grocery store and bought some meaningless string of characters. And so when you interact with a trained model, it becomes apparent that by learning to produce likely next characters that assemble to coherent text continuations, the model's learned a lot about the world. It's learned that the capital of Germany is Berlin. It's learned that Tuesday is the day after Monday. It's learned that grocery stores sell chickpeas, but not yachts. And this brings me to the main question. Since these large language models learn about the world by guessing next characters in pieces of text, knowledge of the world must be encoded in probability distributions on next characters. So that is, seeing that knowledge and rules for reasoning about that knowledge are encoded in probability distributions of next character continuations, the question becomes, how is this knowledge and how are the rules for reasoning about this knowledge encoded? So schematically, you have something like this. You input probability distributions on sequences of text. That's what you have. And then you can produce coherent text continuations, almost by definition. And to produce coherent text continuations is an ability which requires knowledge and reasoning. Being able to tell stories implies that there's some knowledge there and some reasoning. And these large language models prove that this passage that I've drawn schematically is possible in the real world. And so if it's possible in the real world, it's possible to implement this passage in the real world, there must be some theoretical mechanism for producing knowledge and reasoning from distributions on text. So the question is, what is this mechanism? How can we understand the way meaning emerges from sequences of symbols? So I want to emphasize that this diagram is independent of large language models. It's a diagram depicting a purely theoretical passage. So you could ask us similar questions about human knowledge and reasoning and how those things arise within human beings. What is human knowledge? How do people reason? If, for example, you know that dogs can bark, where is that knowledge? Where did it come from, and where does it reside now? If you know not only that dogs bark, but that they bark at mail carriers, and the mail is delivered at 2 p.m., maybe you'll expect to hear barking at 2 p.m. So how is that reasoning performed? This human version of the question is extremely interesting, but it's far more complicated because the nature of human knowledge is mysterious and complex. And practically speaking, when I look at this schematic, we have no idea how to think theoretically about the inputs for human knowledge. Here, when I'm thinking about these large language models, the inputs are clear. It's probability distributions on text sequences. So to take as an example, piece of knowledge, the fact that dogs can bark. So humans have eyes and ears with which you might see a dog, ears that you might hear it bark. So a human might be told by a teacher in school that a dog is an animal that barks, even if they've had no interactions with dogs. So to think about human knowledge and reasoning, requires, you might think would require us to account for all these possible complex and interacting inputs, that might need to be considered for the production of the knowledge that dogs bark. But the fact that GPT-3 learns that dogs are animals that bark, as evidenced by many story continuations featuring barking dogs, this presents us with a clean, much more well-defined math problem. Let me put the schematic back up. So here the input's purely mathematical, consists of just probability distributions on sequences of symbols. It includes nothing like eyes, ears, school teachers, and yet we know that there must still be some passage to a form of knowledge and a form of reasoning. So This implies, for one thing, that eyes, ears, and school teachers aren't required for the acquisition of this kind of knowledge. Furthermore, it's my view that by attacking the mathematically framed question, we might shed light on the knowledge of human knowledge and human reasoning, how it's different, or how it might be similar to the knowledge you can acquire from distributions on texts. Okay. Now I want to emphasize one more thing before we get back to this main question and the mathematics of how knowledge and reasoning are encoded in probability distributions on text continuations. It's a little subtle, but I think it's really important not to take it for granted. Namely, the ability to continue stories can be learned by seeing examples of stories and just trial and error. And this is, I don't think, should be taken for granted. See, not everything can be learned by exposure to examples or simple trial and error. For a seemingly silly example, you can't learn to give birth to kittens by trial and error. I mean, you might consider this example silly because, well, obviously you need biology to give birth to kittens. If you don't have the biological mechanisms, you'll never manage to make kittens. But I think it's completely reasonable to think that you might need biological mechanisms to complete stories. If you want to complete a story about an apple, doesn't it make sense that you might need to know what an apple is? You might need eyes to see the red color. This picture, by the way, is from Wikipedia. This is a wine sap apple, which is my favorite variety here at local New York wine saps. Anyway, maybe you need eyes to see this red color, or taste buds to taste the juicy and tart sweetness of wine saps. Maybe you need hands with which to pick it from the tree. Maybe you need teeth to bite into it and to feel it crunch. An agent that will write coherently and convincingly about apples might need to have something already inside itself that it brings to the story writing. That the something it brings to the story writing might need to be biological. It is not a niche idea. Biolinguistics, I think, is one of the most active and important areas of linguistic research today, and not just today. Here, take this famous course book in linguistics by Saussure. You see the picture on the front cover. I think this is from the late 1800s. It illustrates language originating in the brain, moving out through the mouth, traveling through space, into the ear, and then into another brain. And inside the book, you have lots of other figures like this one I took a picture of on the right, which makes reference, there's a lot of pictures that make reference to biological mechanisms of speech, hearing or comprehension. The idea that biology is an essential component for language production, it isn't a fringe belief. People thought that in order to think about language, you had to think about biology. Now, again, because I think this fact is so important, let me try to further clarify with a thought experiment. So imagine going back to 2015. So 2015, because 2015 is before transformers and before these large language models exist. But it's not so far back that engineers weren't super confident in technology. Imagine an engineer in 2015 is given the task to program a computer to write story completions. Now, the engineer is pretty confident that biological mechanisms aren't required to tell stories. So the engineer sets forth on her task. And as she thinks about it, she realizes, well, to compose a coherent story that begins about golf, for example, the machine ought to know some things about golf. It should know golf is a game. It's played outdoors. It's played during the day. As human players, they use clubs. There's a little ball, and so on. So the engineer concludes that all these facts about golf must be programmed in to write stories about golf. And countless other facts about the world will need to be programmed in too, because, in order to continue stories coherently that begin with stuff in the world, you obviously need knowledge about that stuff and some idea for how to reason with that knowledge. Now, back in 2022, we see that this fictional engineer from 2015 is only half right. She's right that biological mechanisms aren't required to create story continuations, but you also do not need to program in any explicit knowledge about the world. In 2022, we know that an agent can learn to continue stories just by seeing examples and trial and error. The knowledge and the reasoning aren't programmed in. They're still necessary to continue the stories, but they're acquired free, so to speak, by just learning to predict next characters. And I think this is a surprising fact that we really shouldn't take for granted. Okay, so now how can we attack this main question? Now that we know it's possible to extract knowledge and reasoning from distributions of text sequences, and there's no need for an external agent that knows about the world to be involved, how precisely can it be done? See, in math, you don't always know whether something's possible or not, right? Settling a conjecture can be really hard because you don't know whether you're trying to construct a proof or you're searching for a counterexample. But if you know something's true, well, then you can really just focus in and try to discover why it's true and find the structures at work behind the scenes. Okay, so I think it's helpful to have in mind some kind of theory of semantics, a theory of meaning that structurally fits with probability distributions on text continuations. The theory of dynamic semantics comes to mind. The slogan of dynamic semantics, according to the Stanford Encyclopedia of Philosophy, is that meaning is context change potential. That is, the meaning of an expression is the set of possibilities it creates, all the possible continuations, if you will. Then this potential changes as the expression is continued, and potentially, potential continuations become impossible or at least unlikely. And then that sharpens the meaning, and certain further continuations emerge as more likely. I think this is beautifully explained by the great writer George Saunders, writing in this book, A Swim in the Pond in the Rain, about the art of fiction. Saunders writes, a story is a linear temporal phenomenon. It proceeds and charms us a line at a time. We read a bit of text, and a set of expectations arises. A man stood on the roof of a 70-story building. Aren't you kind of expecting him to jump, fall, or be pushed off? You'll be pleased if the story takes that into account, but not pleased if it addresses that too neatly. So that's what George Saunders said, and I think it's brilliant. We read a bit of text, and a set of expectations arises. We read some more, those expectations are revised. if we read something a little bit unexpected, that turns out to be really meaningful. If, we're not pleased if everything happens exactly as expected, because then we've spent our time reading what we already knew, the expectations we already had, and no information has been transferred. So let's try to make this idea more mathematically precise. So this brings me to mathematics and to category theory in particular. Misha Gromov, speaking about category theory a few years ago, said that it far exceeds in its expressive power anything even imaginable, say, before 1960. I chose to cite Gromov here because it was from Gromov that I first encountered the idea that category theory, for which I already understood its awesome expressive power in algebraic topology, might be helpful also for expressing something new about language. So category theory, for those of you who might not know, it's a branch of mathematics that concerns objects and relationships between objects. Here I've pictured some objects as blue dots and relationships between them as arrows. My colleagues and collaborators, Ty Dene Bradley and Yanis Vlasopoulos have written independently and together with myself about using category theory, enriched category theory, in fact, as a framework for studying language. So you can think of language as a category whose objects are the texts in the language, and you specify that one text is related to another if the second text is a continuation of the first. So here's a little piece of this language category. So you have, red is contained in the expression red ruby. So you have an arrow from red to red ruby. You have an arrow from red ruby to bright red ruby, and so on. Now, this category can be enriched by decorating the arrows with probabilities. So, if there's a 1.3% chance of seeing the word ruby after you've seen the word red, you decorate the arrow from red to red ruby with a 0.013, and you get a picture like this. Now, in category theory, relationships between things are the most important things. Objects are determined by their relationships with other objects, and a nice mathematically precise form of this fact is a theorem called the Yonay Dilemma. So in the context of this language category, the Yonay Dilemma asserts that the expression red is determined by all the expressions that contain red. I think this fits nicely with a kind of use theory of meaning, namely the meaning of something is determined by how it's used. So here the meaning of red is the set of all the expressions that contain red as a subtext, and more precisely, it's the set of expressions that contain red together with the probabilities of seeing those expressions conditioned on the fact that red is a subtext. So if it's normal to encounter red ruby but unlikely to encounter to borrow an example of Ty Dene's, if it's unlikely to encounter the idea red idea, that expression, then you want to keep track of this information of what's likely and what's not likely, because that all contributes to the meaning of the word red. So the Yonay Dilemma then gives a passage from text to the meaning of that text. And yeah, I mean, I think you could qualify what I mean here when I say meaning as a use theoretic sense, but I think it's a good sense for meaning. If you know everything that's ever been said about red, then you basically know what red means. You might think that you have some internal representation of red that serves as a version of its meaning, but I can't really verify that your internal representation agrees with mine. Except possibly that everything I might say about red accords with everything you might say about it. In your head, for all I know, red might look blue, or red might look to you the way blue smells to me. I don't know. Or maybe we'll learn that the internal representation you have for red is really a device that accounts for the possible ways that red can be used. Okay, moving on. So if we apply this Yonay Dilemma idea to the entire category consisting of expressions in the language, we arrive at what I call the semantic category. This semantic category includes all the meanings of all the texts as given by this Yonay dilemma in a use theoretic sense, together with higher concepts represented by certain functions on categories of texts. More formally, what I propose for the semantic category consists of sheaves on the language category. In this semantic category, you can build concepts and you can do some reasoning. Here's a picture of the paper, An Enriched Category Theory of Language, with Bradley and Vlasopoulos, and we write about the semantic category in this paper and the intrinsic tools that exist there for building higher concepts and reasoning with them. Without going into too much detail, I'll just say that sheaves on a category forms another category with a bunch of special properties. Namely, the category of sheaves is a topos, delightfully the namesake of the Institute, and topos is known to be an appropriate setting for logic. Here's one of the several famous books about topos theory and the role that sheaves play in logic. In the Enriched Category Theory of Language paper, we have to adapt some of the classic topos theory since the relationships we're interested in are enriched over probabilities. But the basic idea is that the kind of reasoning one can do internally from text is something like categorical logic plus probabilities. That is, if you consider a universe that includes all human language text, but nothing else, then inside this universe, there's a kind of internal logic that allows you to build concepts and reason with them. And this internal logic is a kind of categorical logic enriched with probabilities. Here are some other papers that have also studied this kind of categorical logic enriched with probabilities. I don't know whether they might be too small for you to see, but on the upper left, there's metric spaces and generalized logic and closed categories by Levere. In the middle, there's a paper about tight spans by Simon Willerton. On the right, there's fuzzy concept analysis by Jonathan Elliott. In the middle, on the bottom, is categorical semantics of metric spaces and continuous logic, a little clip from the web by Simon Cho. And there are probably many others as well. Okay, now, why should anyone care? Well, we have these AI systems, these large language models that have learned a lot about the world. It would be nice if we could directly access that knowledge for purposes beyond the the rather slender application of story completion. It would be great, for example, to have some kind of geometrically relevant map of the world knowledge that's learned by a large language model. This is still work in progress that I and the collaborators that I already mentioned, together with some new collaborators like Samantha Jarvis, who's a PhD student in math here at the CUNY Graduate Center. But I think having a relevant picture for the knowledge learned by a large language model, together with an idea about how to formally reason with that knowledge, I mean, this would really change the world. You know, instead of search, which is the way humans now interact with information most commonly, people could interact with information in a more oracular fashion. You ask an oracle questions and you get reliable answers. You provide oracles with different pieces of text and you say, given these, how could you reason and make some conclusions? Okay. Now, I want to end with here the last section of the talk with another set of ideas. Another idea I think is very helpful for thinking about language, especially when you're thinking about engineering new large language models, is physics, in particular quantum physics. For 100 years, physicists have been developing a theory of relationships and probabilities in which systems of interacting building blocks, like letters in the alphabet, each with a finite number of discrete states, give rise to some spectacular macroscopic properties. And from a certain point of view, language looks a lot like a one-dimensional system of interacting quantum particles. Text data has some very particular kinds of statistics, statistical properties. Like, for example, there are very long-term correlations in text that are unlike the kind of correlations you see in other kinds of data sets, like image data sets. From a purely statistical point of view, the statistics observed in text resemble those that are observed in certain quantum systems. So the fact that Melville's Moby Dick begins on page 1 talking about the sea, and then on the last page it's talking about the sea. From a statistical perspective, this is a lot like the fact that the particles at one end of a magnet, their spin points in one direction. That's the same direction as particles at the other end. So you can make this analogy theoretically precise by identifying each character in a text as a quantum particle. Whether you think of these dots as quantum particles or as characters in a text, there's a mathematical formalism that you can use to describe the probabilities of seeing this sequence of objects in a certain configuration. Now, okay, I made a slide with the number 2 on it, but the mathematical formalism involved in describing a quantum many-body system is actually pretty simple. It's like pre-1960s math. It differs from ordinary probability theory in some ways that are quite innocent. Like there's an exponent of 2 in certain places, where in ordinary probability, you might find an exponent of 1. But one distinguishing feature of quantum probability is that it provides for entanglement. Now, this remarkable feature allows information about a subsystem to know about the possible arrangements of the complementary system. So in the context of language, it means that the representations of individual texts know about the possible continuations of those texts. That is a model for language as a one-dimensional system of interacting quantum particles is very compatible with this categorical perspective for language that that I already advocated for. And now again, why should you care about this? Well, simulating quantum systems is notoriously difficult, right? It's what people want quantum computers for. But there are new methods in computational quantum physics that have been developed over the last decade that have made it possible to store and manipulate extraordinarily high dimensional data in efficient ways. So I'm talking specifically about something called tensor networks. Computational quantum physicists like Miles Studenmeyer and Stephen White, Geoffrey Vidal, and other people, notably the computational, the CCQ group, the Center for Computational Quantum Physics at the Flatiron Institute, have been able to use tensor networks to design algorithms for certain linear algebra operations with polylogarithmic complexity. So that's exactly the kind of exponential speedup you would get from using a quantum computer to do linear algebra. But with these tensor networks and these tensor network techniques, you're able to get that kind of speed up with a classical computer. I mean, this is more than just a speculative idea. Language models using tensor networks have been built that perform exactly as the theory would predict in small academic experiments. No one's ever built a large language model based on these ideas. And there are significant engineering hurdles to doing so. But I mean, the field is advancing. I'll mention Konstantin van der Poels. He's a physics graduate student here at CUNY's Initiative for Theoretical Sciences, who is one person working to advance these ideas. You know, I think it's worth keeping alternative architectures for large language models in mind. You know, as is often pointed out in the many popular press articles about transformer-based large language models, such as this article that was from like last week by Stephen Johnson in the New York Times Magazine. It's like 13 pages long about GPT-3. You know, this article and lots of other ones talk about how existing large language models have shortcomings. And it's possible that transformer-based large language models may have limitations. You know, there may be limits to how much better they can get by just throwing more metal at them, just making them bigger and bigger. I mean, for one thing, these models are incredibly inefficient. They require a huge amounts of energy. You know, it takes tens of millions of dollars worth of electricity to train and run them. You can ask yourself, is a massive amount of energy required for language skills? Absolutely not. I mean, the human brain runs on about 20 watts. That's the same amount of energy to light the dim bulb in your oven. A back of the envelope computation for GPT-3, you know, they published, you know, how many processors they used and what the training times were, you know, implies it took about 1,000 megawatt hours to train. So, I mean, just to put that in perspective, you can compare that to the yearly energy consumption of a typical US household, which is like 10,000 kilowatt hours, or the 8,000 megawatts that are consumed in New York City every day. 8,000 megawatts is a little bigger than one, but you know, in New York City, you're moving people, trucks, elevators, you know, construction devices. I mean, you're actually moving physical matter. It's insane that those are on the same order of magnitude. Insane to me, anyway. So this is my last slide, and I'm just adding that to conclude that if transformers prove to have fundamental limitations, perhaps ideas from quantum physics might help get over those limitations. So thank you for your attention. I'm going to change gears and check the chat now and see there are some questions.
Well, thanks, John. A bunch of, we did have some questions. I think Tim has raised his hand. Tim, you want to ask a question?
Me to ask? Okay, I'll ask now. First of all, thanks. It was a great talk. So one thing that I want to so you mentioned this idea of this Yoneda approach to meanings of words, and it's really nice, but I struggled to reconcile this with how language is used across different communities. Say I run into some Spanish speaker and I'm like, oh, I know what a cat is. He knows what a gato is. So we're like, okay, we've got the same word. But then I look at my Yoneda language category and I'm like, okay, so I have a non-zero probability to get into the phrase raining cats and dogs. And the Spanish speaker doesn't have that. And I've got cat on a hot tin roof and the cat's mother and, all these things. And we start to think, well, are our meanings of cat different? Because I have big probabilities here. You have 0 ones. But to me, a cat still means the same thing as it does to them. It's just the way that idioms in language work, it doesn't always reflect this. So I'm wondering, how can you reconcile that with this Yoneda point of view?
So thank you, Tim, for the question. So my first reaction to that question is that there's would be some kind of functor from a language category created out of English expressions into this semantic category, and another one from Spanish language expressions into this semantic category. And it would be in the semantic category where you could sort of compare the ideas. Now, in practice, actually, a lot of, GPT-3 has seen a lot of Spanish text, and you can, give it a story that has some English and has some Spanish in it, and it kind of handles it effortlessly. So I think this ability to change context is already present if you really are getting these probability distributions on sequences correctly.
Okay, thanks.
Yeah.
Looks like Lee was next.
Lee.
Am I unmuted?
You are not muted. I can hear you.
Okay, great. Thank you. I love this talk. So my question is, for years I have been fascinated, as have many others, with the question of, will it be very increasingly productive to look at biological processes as language systems, not merely chemical physical systems? And so, the whole area of research under the notion of biosemiotics looks at this question. And how, if there is such a thing as a language being spoken, how do its signs create meaning? And those questions seem to me to be so much aligned with yours. So my question is, do you have an interest in this so-called biosemiotic investigation of language?
Thank you. I don't know much about biosemiotic questions of language, but I think that, but it reminds me that the way I'm trying to think about it myself is that there could be lots of different mechanisms. There's no doubt that that a transformer architecture has a certain structure inside of it, and it's producing probability distributions on continuations by some mechanism that's internal to the computer, and biological. And then there's certainly humans have biological ways of producing text continuations. And so I sort of think that there must be some theoretical passage that might be helpful for understanding either of the the instances in different implementations, and might even do some might even help people address questions that they're struggling with it in those particular fields.
Yeah, I could include, or because I was thinking in advance of your talk, 2 or 3 links to some recent papers. If you're interested, I could paste that in.
Yeah, put them in the chat, please. I think everyone would, and myself included, would appreciate that.
Thanks so much.
Great. We had a question before I get to Andreas. Eva, I think, was asking a question in the chat. Maybe I'd like to give that.
Which question in the chat?
Well, I think Eva might, yeah.
I can ask if
Oh.
it's easier. This is thank you for the talk, by the way. This is a very basic question. It's something I've wondered, and I should probably read a bit more about myself. But every time you refer to this this relationship between quantum physics or many-body systems and language, are you generally talking about finite Hilbert spaces? Because with category theory, this is most of what I've seen is finite Hilbert spaces. The continuous spectrum doesn't really seem to be a thing. And A, why is that? And B, is it the case that you only really look at finite systems? And what does it imply? Is there any interesting thing to say about that?
Yes, so thank you. I think I'm just thinking of finite systems. So the way I would think about it, the dimension of the system is I would think of each character in a piece of text as one particle that could take 2 positions. I mean, you could do the whole theory of language in a binary way, 0 and 1, or maybe each particle takes 256 positions, you know, like Unicode or something. And then, so the state of one character would be a vector in a 256 dimensional Hilbert space. But in a sequence of n characters, it would be a vector in a Hilbert space that would be the tensor product of those basic atomic Hilbert spaces. And so as long as you don't have infinite text, and there's never been an infinite text produced by humans, then I think you can probably get away with just thinking about finite dimensional Hilbert spaces.
Okay, that's really helpful. Thanks. I think I was more thinking in terms of the vagueness or nebulous nature of language, and how maybe in terms of observables, more like you would have some notion of, you know, here's a continuous spectrum of what this word can mean in a sense. But this is very abstract, like very philosophical more than practical.
Right. I mean, I think there are a lot of other ideas about, you know, quantum physics and language out there. In fact, just even physics and language, right? You know, 75 years ago, Claude Shannon was thinking about, you know, co-opting the ideas of entropy to talk about Shannon information, which, you know, produced information theory, which is, I don't need to elaborate on the importance of that. And I think other people like, you know, Penrose think language is the product of a human brain which occupies a macroscopic quantum state. So language is literally the observations, the measured observations we see from a quantum system. You know, you don't actually need to have, you know, I think that there's a lot of interesting ideas out there, but if you're just thinking about the mechanics from a very practical perspective about probabilities and how they work to sort of you know, make text predictions, then you can find the ideas, just the mathematical framework of quantum mechanics can be useful in a way that's independent of any of its more you know, provocative ideas.
Thank you very much.
Next we have Andreas.
Andreas.
Okay, I have several questions, but let me begin with the last one just to confuse things. About the analogy between language and one-dimensional quantum arrays. That 2 on your slide has, in quantum mechanics, some interesting consequences. For instance, in particular, destructive interference can happen. With this has some probability under these circumstances and some probability under those. And is there a familiar language phenomenon analogous to that?
So I don't know. I think there are people that think about language in terms of and ways in which language is like quantum physics, that think about things like kind of Bell inequality type ideas, and the way I'm thinking of it is a little bit different, and it's not as amenable to examples of saying like, here's destructive interference. I think the real, this idea of entanglement is really important for talking about subsystems and knowing about the continuations. There's and there are a few other ideas that are important. I mentioned the statistics, the correlations that you find in language. Yeah. But I think that the actual way you model it as a quantum system, for example, do you model the system as a pure state? That's kind of the way I'm thinking about it. That you can take, the sum of all possible expressions, and that's basically a pure state. That describes the state of language. You modify this. You calibrate it so that it has the right probabilities, and then so that's sort of how I'm thinking about it. But I don't know about destructive interference. It's a great question.
Okay, can I ask? I'd like to ask a totally disjoint question, just to get a better picture of how good these continuation producing algorithms are. Hypothetically, suppose I trained one of these massive systems on a corpus that contains a lot of good mathematics papers. Mm-hmm. And then I ask it, okay, give me a continuation for the following text. The purpose of this paper is to prove the Riemann hypothesis. Now, presumably we will not get a proof of the Riemann hypothesis that way, but we'll get something coherent, at least for a while. And I guess my question really is, how coherent for how long will it be before it goes off the rails?
Yeah, I think this is a good question, but it's a question that to me is really, it's a question of degree.
Yes,
because
how good is it?
As we all know from using autocomplete with texts, or you have it in Gmail, it works. And a decade ago you had autocomplete, and it kind of worked too. But if you do autocomplete over and over and over, you generally get sort of meaningless things. But and it would be reasonable to there could be an analog to your question asked a decade ago. How good could these continuations be? Could they really tell me a story about going to the grocery store and getting, chickpeas and cucumbers, and would it eventually end up with me going home and making hummus or something like? And the answer is yes. Like, now they do that. And so the question about continuing mathematics, I think, is just a question of degree. I think
I agree. That's really why I formulated the question that way. It's a question about how good are these systems, not how good will they be, because they'll be better. I think it'll be a while before they prove the Riemann.
Well, where
are we now?
So I don't know exactly where we are now. In fact, I haven't done that experiment. People can do that experiment, but there are these, there have been examples where they've shown that GPT-3 can produce correct answers to integration problems that Mathematica cannot produce. So that's sort of mind-blowing.
Yes.
There was a paper in Nature, I think just like a month or two ago, about using something like GPT-3 to produce new math conjectures and then prove them in certain areas of combinatorics. This is a fascinating piece of work, and you should look it up because it's very closely related to your question.
That's a good answer to what I wanted to know, even if it doesn't immediately touch the Riemann hypothesis.
Yes.
Okay, thank you.
Great, thanks, Andreas. We have time maybe for one more question from Sam.
Okay, cool. But before I ask my question, I just want to briefly speak a little bit about what Andreas was asking. Like nowadays, language models can actually produce reasonable looking code, for example, code that compiles, the braces are right and stuff. And if one believes like, the Curry isomorphism, that creating a program of a given type is the same as proving a proposition, then you can actually prove simple things just based on, like your function declaration, but it breaks down. And if you want to learn more about this, you can look at the work of Armando Solisama and Maxwell Nye. And the one other thing is about quantum. I don't know anything about quantum stuff except for the physics of it, but like there is interesting work that uses like sort of non-classical logic, including interesting modal quantifiers in so-called logical induction, which is where you try to assign like credences, which are not probabilities to statements, and ask how they compose. And of course, statistical independence is complicated, so you can't just use and or. Okay, but my actual question for John is like, is there a space for qualia in your framework? For example, the sensation of red, or are you one of those people, and this is very okay, who don't believe in qualia? Like, and by qualia, I just mean like the sensation of seeing red that someone who's a colorblind scientist, say, who has never seen red before, but has a spectrometer installed in her goggles and has read everything about the history of red in art and knows everything about which apples are red and which pears are red, etc. Does she still learn something when she gets an anti-colorblind surgery and sees a red apple for the first time? And if so, is that modeled in this completely relative point of view?
Okay, so thank you for the references and the question. So I don't actually know very much about this, but in a way, it reminds me of a thought experiment by a question raised by the philosopher David Chalmers, in which he talks about, would we, imagine you have a human being who is who does everything that a human being will do and can do, but is really a zombie. In other words, has no consciousness. The question is that being, alive? Or, I don't know exactly how he uses this argument. I think he's using this argument that the idea that we can envision such a thing means that there's something real and about consciousness within us. But yeah, but I from the outside, I don't know. I don't know. So, okay. So your question reminded me of something. I mentioned it. Maybe it's not relevant. Maybe it is. I think it's a good question. Someone recently told me about a fascinating experiment that was done recently, in which you can activate part of a brain and then create a physical gesture like a knee kick, and that for people that they've done this for, and they tell at the onset they insist, okay, I'm not going to kick my knee, and then they stimulate that part of the brain. In interviews afterwards, they say, well, yeah, I decided I wasn't going to kick my knee, but at the last minute I changed my mind.
That's awesome.
Yeah. In fact, it was Yanis Philosophos, who's in the audience, actually. If you have a reference for that experiment, it would be great to share it if you know it. That really was interesting to me. All right, well, thanks everybody for your attention. It was really great to be here.
Thanks again, John. Okay, so we'll stop the recording and the live stream and